Have you ever been stuck on a puzzle that just seems to have way too many possible answers? Well, it turns out that sometimes the most brilliant solution is hiding right in front of you. You need a mirror to see it. So today, we're going to dive into this simple but incredibly powerful world of geometric reflections and see how they can unlock the secrets to some really tricky real-world problems.
Okay, let's just jump right in with a classic puzzle. Picture this. You need to get to the bookstore. Your friend needs to get to the music shop right next door. You can park anywhere you want along that straight curb. So where do you park the car so that the total walking distance, your walk to the store plus your friend's walk, is the absolute shortest it can possibly be? Go on, think about it for a second. It's definitely not as obvious as it first looks.
Now, to crack that puzzle, we first have to get comfortable with the main tool we're going to use. It's a fundamental idea in geometry, and it's all about learning to see the world in a mirror.
So what even is a reflection? Well, it's pretty much exactly what it sounds like. It's a transformation that flips a figure over a line. That line acts just like a mirror, and, you guessed it, we call it the line of reflection. What you get is a perfect, flipped copy of the original.
Okay, let's get into the geometry behind this, because this is the key. Look at point P and its reflection, which we call P'. That line of reflection, M, isn't just any random line. It's what we call the perpendicular bisector. Now, that's just a fancy way of saying two really simple things. One, it hits the line connecting P and P' at a perfect 90-degree angle. And two, the distance from P to the mirror is exactly the same as the distance from P' to the mirror. This one rule, right here, is the key to everything else we're going to do.
So now that we know that rule, let's make it practical. How do we actually do a reflection on a coordinate grid? Let's figure out how to map the flip.
Okay, so here we've got a blue triangle, and our line of reflection is that vertical line at x equals 3. Let's just take point A. If you count the squares, you can see it's 2 units to the left of the line, so its reflection, A', has to be exactly 2 units to the right. Same thing for B. Same thing for C. You just count how far each point is from the mirror, and then you go that same distance on the other side. Simple as that.
And, no surprise here, the exact same logic works perfectly for horizontal lines too. So now our mirror is the line y equals 1. Point A is 2 units above it, right? So its reflection, A', lands exactly 2 units below it. Point B is 1 unit above, so B' is 1 unit below. See? It's beautifully consistent.
Now, counting squares is a fantastic way to visualize what's going on. It really helps you see it. But let's be real. If your coordinates were something crazy, like 100, 52, you're not going to want to sit there counting squares all day. Luckily, math gives us some really elegant shortcuts.
And here they are, the cheat codes for reflections. If you're reflecting across the x-axis, you just flip the sign of the y-coordinate. That's it. Across the y-axis, you flip the sign of the x-coordinate. These rules let you figure out the new position of any point instantly. No drawing, no counting required.
Now let's look at those diagonal lines, which always seem a little tricky. Reflecting across the line y equals x is actually the easiest one of all. You literally just swap the x and y coordinates, so a point like 1, 2 becomes 2, 1. Easy. Now for the line y equals negative x, it's a two-step move. You swap the coordinates and you flip both of their signs.
Okay, so you've mastered the basic flip. Now we can start combining reflections with other kinds of movements to create some more complex and pretty cool stuff. We're going to look at something called a glide reflection and the beautiful idea of symmetry.
A glide reflection is, well, it's exactly what it sounds like. It's a combination of a glide, which is just another word for a translation or a slide, and then a reflection. Think about walking on a wet beach. You take a step forward, that's the glide, and in the puddle next to you, you see a perfect reflection of your footprint. That's the idea.
Now, the order here is super important. First, you perform the slide. You move the whole figure to a new spot. Then, from that new location, you perform the reflection. And one key detail, for it to be a true glide reflection, that line you reflect over has to be parallel to the direction you just slit the object. Let's see it in action. We start with the blue triangle. The instructions say, first, translate it 12 units to the left. Okay, so we just slide it over, and it lands where that red triangle is. Step 1, done. Now, step 2, we reflect that red triangle across the x-axis, and boom! That gives us our final image, the green triangle. Slide, then flip.
Okay, so moving on from complex movements, we find that reflections are also the absolute key to understanding one of the most fundamental principles in nature and art, symmetry. It's all about balance and beauty, and it's all defined by reflections.
So a line of symmetry is basically a special kind of reflection line. If you reflect a figure across its line of symmetry, it lands perfectly on top of itself. It's like it doesn't even move. And as you can see with these hexagons, some shapes, like the regular one in the middle, have a ton of lines of symmetry. Others might have only one or maybe even none at all.
All right, we've gone over the basics, the coordinate rules, even some advanced moves. We now have every single tool we need. Let's go back to that parking problem and finally reveal the secret of the shortest path. So here we are again. You're at point A, your friend's at point B, and the curb is that line M. We're looking for that single, perfect spot C on the curb that makes the path from A to C to B as short as it can possibly be.
I mean, you could try to guess and check, right? Park here, measure. Park over there, measure. But that would be super frustrating, and you'd probably never find the exact spot. But geometry, and specifically the reflections we've just learned, gives us this stunningly simple way to find the answer with total certainty. No guesswork needed.
And here it is, the elegant solution. Let's break this down. Instead of worrying about two different paths, you just pick one of the points, let's pick B, and you reflect it across the curb to get that new point, B prime. Now, here's the magic. Just for a second, forget about the original point B. What's the shortest distance from point A to our new point B prime? We all know that it's a straight line. So you just draw a straight line from A to B prime. And the exact spot where that line crosses the curb, that's it. That is your optimal parking spot C. It works because reflections preserve distance, so the path from C to B is the exact same length as the path from C to B prime. We just turned a complicated two-part problem into one simple, straight line.
So in the end, we didn't break any rules of geometry. We just used them in a really clever way. We all learn that the shortest distance between 2 points is a straight line. What we don't always learn is that sometimes you just need a mirror to find the right 2 points to connect.
And this principle is not just for parking cars. It's used to model the path light takes when it bounces off a mirror. It's used in robotics, in designing efficient networks. It really makes you wonder, right? What other complex problems in our own lives are actually just simple, straight-line solutions just waiting for us to find the right mirror to look into?